Okay, welcome to lab here. So as we just finished talking about a little change in the schedule here. Um, so again, since we're just a little behind because of the first day and all that good stuff, and this lab that's coming up does involve a lot of these sort of calculations that we haven't got to yet. We're going to, again, we're going to do some lecturing here in lab. And I think what we'll do is we'll just move experiment 2 to Thursday, and everybody else just gets pushed back a day. So just look at the schedule basically and just keep pushing everybody back. I think we'll catch back up come like the third week or something like that. So it'll be okay. But that's sort of the game plan. So we'll do experiment 2 on Thursday, and then that would obviously move experiment 3 to the following Tuesday, and so forth all the way through. Okay. So obviously we've been talking about sort of the atom, energy, electrons, waves. So we just did that last example. And again, as I mentioned in the last example, you want to definitely make sure you know how to use your exponent button and you are getting how to punch it in. We're going to do a bunch of examples here, I think, up front or in this sort of part of the chapter where you'll have to make sure you know how to do that, and you'll know very quickly if you are punching it in correctly or incorrectly. And again, if you do need help with that after we're done lecturing here today, I'd be more than happy to help you sort of figure it out on your particular calculator if you still can't. Again, make sure you do put here in the chat box roll if you haven't done so already. All right, so why don't you then continue on? So this should be the next example that we have going. We want to calculate the wavelength here. Let's do the wavelength in meters. So we'll do the wavelength here in meters, and of a radio wave that has a frequency of 100.7 megahertz. Mega is 10 to the 6. So why don't you take a minute or two, again, get the answer. You could put it in the chat box there, and we will then talk about it. Look, so in this case, again, we're looking for the wavelength of a radio signal with a frequency of 100.7 megahertz. So a couple important sort of relationships. We are given, excuse me, we are going to use that same formula that we saw previously, which is C times the wavelength times the frequency. We are given the frequency, which is 100.7 megahertz. We are given, obviously, we have the speed of light. Remember that a hertz is the same as a reciprocal second, but this is megahertz. So we do want to convert our megahertz into regular hertz. So to do that, again, we will use that mega prefix, and you want to make sure that you do get it correctly. So when it says 10 to the 6, that means in one of the prefix, which would be megahertz, there is 10 to the 6 hertz. So base units hertz, prefix is megahertz, and again, that is the correct way to do it. And that basically means that if we take 100.7 megahertz, again, not written like a fraction, but it essentially is a fraction. So doing sort of dimensional analysis, if you remember, opposites to cancel means units needs to go on the bottom. So 1 megahertz will cancel, and 10 to the 6 hertz up on top. 10 to the 6 is essentially 1 times 10 to the 6, if you want to punch in that. And again, a reminder that we're multiplying everything up on top, and we're dividing by whatever's on the bottom. And in terms of units, if megahertz is up on top and megahertz is on the bottom, they cancel each other out to 1. Same idea as you divide 2 by 2, you get 1. So units, opposite locations cancel each other. And if we multiply that out, looks like we end up with 1.007 times 10 to the 8 hertz. Again, with that relationship that our hertz is the same as a reciprocal second, that means that we have 1.007 times 10 to the 8 reciprocal seconds. Any questions up to that point?
I have a question. The
Yeah.
last one we ended in nanometers, and
Right.
this one was in meter. Is the last one nanometers because we started off in scientific notation?
It's actually nanometers because of and it'll probably make more sense in one or two, maybe one slide down the road. But this really has to do with sort of the electromagnetic spectrum that we talked about the other day. And radio waves are longer waves. So usually they're kind of given in units of meters and stuff like that. Well, the previous example, we were looking for red light, which is part of the visible part of the spectrum. And the visible part of the spectrum is oftentimes given in terms of wavelengths as nanometers. So that's really the reason why sort of the difference in units is really where this particular wave is coming off in terms of its normal sort of wavelength. And it definitely will tell you in problems usually, give the answer in meters or nanometers or something like that. But that's the real reason is because the radio wave is a much longer wave. So it again will usually be given sort of in the base unit, while visible part of the spectrum is a very small wave, and otherwise you'll have a ton of zeros. So the last one was like whatever it was, 6.94 times 10 to the minus 7. So instead of having to write all those zeros for something in the visible spectrum, usually they give it in nanometers. It kind of makes it a more of a whole number. Other questions on that? Okay, so now that we have the frequency, and again, the purpose really of doing this conversion is to get it in the proper units, to get it in the reciprocal seconds so that it will cancel with our speed of light. Also, if you look at the units for our speed of light, we see meters, right? So that also tells us that sometimes the wavelength may not be given to you in meters. So you do have to kind of convert it to meters if you're going to use the speed of light, like in the previous calculation or something like that. So you want to make sure you watch those units so you're not off by a factor of whatever you may be looking for. So we're looking for the wavelength here. So we want to divide that to the other side. So that's going to give us the wavelength is c divided by the frequency. Again, using our speed of light, meters per second, divided by our 1.007 times 10 to the 8 reciprocal seconds. Again, seconds on the bottom. Reciprocal seconds means 1 over seconds. So when you divide it, the seconds ends up on top and they cancel. And that ends you with 2.98 meters, which is what I saw in the chat box there. So that's good. And again, really, as to the question earlier, it's in meters because it is part of the radio waves, part of the electromagnetic spectrum, and it has a kind of longer wavelength. Any questions on that calculation there? And again, you want to make sure you do use those exponent buttons for sure. Otherwise, you will find yourself probably off on a lot of these calculations. Any questions on how to calculate the wavelength, the frequency, any of those things? And again, these type of conversions where we use those prefixes, super common. People always reversing these incorrectly or using them incorrectly. And again, that's the same as 1 times 10 to the 6. All right, so let's then talk about, hopefully they agree with me, there you go. Let's talk about sort of the nature of waves, and we touched upon it, I think, in that previous experiment last week. But there is a relationship between waves and really frequency and sort of energy associated with them. So as we talked about before, here are 3 different waves. One's a red, representing red light, green light, and blue light. And these are all part of that visible part of the spectrum where we do see colors. And that relationship, to remind everybody, is in terms of the wavelength. If we have a short wavelength, that usually means we have a higher frequency. And that usually results in higher energy, as we talked about. And vice versa, if we start with a wavelength that is longer, we have a lower frequency. And that usually results in lower energy. And we can kind of see it with these waves that are drawn. The top one here, which is the red one, you can see the wavelength is, from here to here. For the green light, it's a much smaller wavelength, and it gets even smaller down here on the blue light. And you can see that, the red light's kind of drawn out, not occurring as often. Green gets a little bit better, not as drawn out in terms of the wavelength, happening a lot more frequently. And here at the end, we have this wave that's really just vibrating through space very, very quickly. So in terms of colors, we could even again put our colors in terms of energy as well. The red we would expect to be lowest in energy, again, because of that sort of longer wavelength, as opposed to our blue guy here, which is going very quickly, be higher in energy, right? So you kind of think about it, something is approaching you and it's kind of moving really kind of slow to get to you or wherever it may get. By the time it may get to you, it's probably not going to be carrying a lot of energy, right? If we were to sort of hit something, I suppose, as opposed to something where it's just repeating really, really, very quickly. As you can see, it's kind of going across very quickly. It's going to carry a lot more energy associated with it. That's a very bad demonstration of a wave, but I think you get the idea. So remember, in terms of our sort of colors, our Roy G. Biv, right? Red had the longer wavelength, and again, lower in energy, as opposed to the more violet colors, which has a shorter wavelength and higher in energy. Any questions on that? So as we're talking about sort of this energy moving through space in the form of these waves, there's different amount of energy that's available or can do different amounts of things. This is the electromagnetic spectrum. In terms of the wavelength in meters, this is 10 to the fourth, as opposed to 10 to the minus 12 on this end. So this is our lambda, and 10 to the minus 12 is basically 12 places to the left with a bunch of zeros, a very, very small number, as opposed to 10 to the fourth, which is 4 places to the right, which is a lot more larger number. So in terms of energy, this has a much smaller wavelength, and this side should be higher in energy, as opposed to over here where we have a longer wavelength, and this side should be lower in energy on the right hand side. So if we go all the way to kind of the right hand side here, we have radio waves. So like when we're listening to the radio in the car, and what we just did, you can see it's on the order of hundreds, as we, so we got 2.98, which is pretty good in terms of radio waves. Not a lot of energy. Then if we move down, we have microwaves. So this gains a little bit more energy, enough to again make sort of water molecules spin really quickly in your food and cook it. Infrared, that's usually where we kind of feel like heat coming off. This then goes into the visible part of the spectrum. So as we talked about last time, that again is where we see color. And obviously that's our red on this side and our violet on this side. And again, going from red to violet, we are increasing energy and decreasing the wavelength, or it's getting smaller. Ultraviolet has a little bit more energy. It's why obviously we put things like sunblock on, right? So we don't get too, kind of damage and stuff like that from their very strong waves. X-rays, again, more energy, as we talked about last time, why they exit the room and kind of put a lead vest on you when they give you X-rays. And gamma rays, we talked a little bit about whether we talk about Rutherford. Gamma rays is basically just pure energy. It's basically radioactive sort of rays that have no charge associated with it. Very, very high in energy. So you do need to know this electromagnetic spectrum. What you need to know about it is not necessarily where each of them come out in terms of wavelength. So, I won't ask you, what is the wavelength for microwaves or something like that. But you do need to know it in order of like, this is the highest energy to lowest energy, longer wavelength to shorter wavelength, higher frequency to lower frequency. So kind of like that pre-lab question from the first experiment, kind of putting everybody in order. In addition, you do need to know the order for our colors as well. So you need to know that red is longer in wavelength, lower in energy versus, say, the violet side or the blue side, which is shorter in energy and shorter in wavelength and higher in energy. Any questions on what you need to know? So again, you don't need to know exact numbers, but you do need to be able to put them in order and also be able to put the colors in order in that sort of fashion. Any questions on that? That's a pickle. That's good. Good talk. So let's talk a little bit then about energy. So when sort of these electrons transfer from one energy level to the next, they basically gain or lose energy in really what is sometimes referred to as certain whole number multiples, and is what is sometimes referred to as like a quanta of energy. And I'll put my HV over here. So it is sometimes given off in the multiples of h times the frequency. And that it gives us an equation which is important. E equals h times the frequency. H is Planck's constant, so it is a constant. And it is 6.63 times 10 to the minus 34 joules times second. So that, again, much like the speed of light, is a number that you sort of always have sort of available to you. So really what this sort of means is, if you have our electron like we were talking about, it's going to perhaps gain energy, enough energy to go from this energy level it's at all the way up to, say, the next energy or 2 energy levels above. You will never sort of find a spot where it gains energy where it's just like, well, I'm good. I'm just gonna kind of hang out here in between 2 energy levels. So it's kind of like when we talk about sort of the idea of quantized energy or a packet of energy, it's kind of like an example of like stairs, for example. When you walk stairs, typically, you have enough energy to go from, one step to the next. You don't usually find yourself like, I'm only going to stop halfway between the step and take a rest or something like that. So you usually have enough energy to go from one step to the next. And that's the idea here behind quantized energy. You have enough energy to go from one energy level to the next. Other people that kind of walk stairs could sometimes have enough energy to go 2 stairs at a time, right? 2 steps at a time, 3 steps at a time. No, 4 steps. No, but at least 2 or 3 steps at a time. Some people can do, right? They have enough energy to go all the way from, say, the first step to the 4th step or the 3rd step, while some people have enough energy to go from first step to the second step to the 3rd step, and so forth. So when we talk about these electrons gaining and losing energy as they transition from one energy level to the next, that's essentially what we're talking about. We're talking about them having enough energy, again, to go fully from one energy level to the next. And that means both ways. So when they gain energy, they go to higher energy levels, or when they lose energy and they go back down to lower energy levels, they go up and down in that same fashion, enough energy basically to kind of go from one to the next. Any questions on that there? Now, when we talk about energy and we just look at this formula here, and in terms of units, Planck's constant has units of joules times seconds. Remember, frequency is reciprocal seconds, which means when we multiply these, the seconds cancel, and we end up with units of joules when we use this equation here in terms of calculating the energy associated with a wave as it is sort of transitioning or moving. Now, using this equation and the one that we saw previously, we really can sort of put them together, and it gives us some ways to calculate certain things. So if we take the one we just saw, which is our energy is h times the frequency, our c is the wavelength times the frequency. If we solve for the frequency, which is c times the wavelength, we can substitute this into this equation, and we would get E is equal to hc divided by the wavelength. And this is a very useful sort of formula because it essentially allows us to calculate the energy of a photon, which is basically that light that's coming off as, let's say, electrons transition. And the nice thing is the top part here, they are both constants. So H again is that Planck's constant, which you always have that number. C is always the speed of light, which you always have that number as well. Which means what this allows you to do is if you simply know the wavelength, you could calculate the energy associated with it. By the way, when you use this wavelength in this equation, it does need to be in meters so that it will cancel out correctly with the units that are there. Also, as well, if we know just the frequency of the wave, you could figure out the energy. So you could use these formulas sort of interchangeably. And again, it allows you some flexibility. If you happen to only know the wavelength, you could still figure out the energy. If you happen to only know the frequency, you could also figure out the energy. And obviously our original one here allows us to figure out either the wavelength or the frequency, depending on which one was given to you. Any questions on that there? So you can really use a couple of variety of ways to figure out if you're asked what's the frequency or what's the wavelength. There's a few different sort of ways you could kind of calculate those depending on sort of the path you choose. They all should sort of end up the same. Any questions on that? So energy, through this equation here, E equals mc squared. That's our good friend Einstein. And that is the mass. And again, that is our speed of light. And a lot of what experiments came about, and for example, Einstein did the photoelectric step. He did what is referred to as the photoelectric effect. Basically, he shined light of different wavelengths on pieces of metal. He was able to find that, the metal is able to basically eject off electrons from the surface of the metals. And a lot of that sort of experimentation, along with some others, brings up what we oftentimes talk about is sort of the dual nature of light. And basically, it's this idea that, there's basically two things. There's basically particles, like electrons and things like that. And, there is basically waves. And, particles can have wave-like function, like things like electrons could behave very much like how particles sort of behave, but they also do share sort of wave type function, which is really important as well. So we talk a lot about the dual nature of light, and we see it come up, and a little bit later we'll talk about it a little bit more, but it's this idea that, particles can have properties that are very much like waves, like wave lengths and stuff like that. And again, waves could have very much particle type properties as well. And that dual nature of light gives us, when we look at sort of what's happening as these electrons are transitioning and energy is being given off, or in general situations, it usually results in really two types of spectrum that we oftentimes will sort of see occur. One type of spectrum is what is referred to as a continuous spectrum. So a continuous spectrum essentially is, for example, it contains the wavelengths, all the wavelengths basically, sort of come off at once. So we sometimes will see this sort of in terms of color. If you look sort of at a spectrum, I want to say maybe more of like a rainbow color, but there's really no distinct spots along the ways because every sort of wavelength is coming off in these sort of spectrums. And that's usually what we see with something like the sun, when metals are sort of heated and stuff like that. But something else happens when we heat, say, an element, for example, and it gives an emission spectrum. We oftentimes will see what is sometimes referred to as a line spectrum. And in a line spectrum, pretty much like it implies, what we see is not like everybody coming off at once in the continuous spectrum. We see really distinct lines occurring at different wavelengths. And for example, if they're in the visible part of the spectrum, they correspond to a different color, for example. If this was the visible part of the spectrum where they came off. Doesn't necessarily mean they have to come off in the visible part of the spectrum. They could come off in like the infrared, the UV part of the spectrum. But this is sort of where we see sort of those colors come off. How do we do this? Well, one way we could do it is, like the flame test, sort of. But another very common way is like do an electrical current, for example. So if you have a lamp that has like an element in it and you run electrical current through it, it's going to excite all of those electrons, just like in a flame test, to higher energy levels. And as they come back down, they're going to basically come back down to different energy levels and give off light in a specific wavelength. And if you look through sort of a prism, you'll be able to really see these lights basically come out as these distinct lines. And what do these represent? Well, again, they represent the idea that quantized energy, and again, sort of an example is like stairs. Again, as I mentioned, if you're on this step, you're going to, if you're an electron, for example, get to the next step. Again, maybe you're able to do 2 steps at a time. You won't find yourself in between or anything like that. And sort of the idea of continuous spectrum happens when we don't have that. So, for example, let's just say we had not stairs, but we just had like a ramp, and you started here. Imagine this is higher up, and this is the bottom of the ramp. If you walked at the ramp up a hill, you technically could stop, anywhere you like along the way, and you would have wavelengths coming off all the way across because you could sit there. It's on a ramp. It's not a step. Again, you can't, if you're doing a step, which is more quantized in terms of energy, you can't just hang out halfway between the step without probably falling back down, to the lower energy level or something like that. So that's sort of the difference between a quantized level of energy, which is what we see when we take elements and we sort of heat them up, and they give off that, as opposed to something like, again, the sun, where it's more of a continuous one. We see light coming off of all colors. We do see energy and heat coming off. We have things coming off all the way across that electromagnetic spectrum. And again, it doesn't give us this distinct sort of line spectrum. The nice thing about a line spectrum, for example, is every element has its own unique line spectrum. So depending on where you see the lines come out, what colors you see, what the wavelengths are, you could look at it and go, that looks like hydrogen, or that looks like neon spectrum. It has different lines at different, wavelengths, and may share some similar colors, but they're at different spots along the way. Any questions on that?
I was curious why the rainbow is always the same order.
Yeah, so it's sort of it's a good question. It has to do with, I think, in terms of the wavelength and in terms of those colors, right? It's basically kind of a reflection, right, of like the water and all that kind of stuff that happens, right? And it goes through sort of a prism. So it's just like when you look at through a prism, you'll see sort of like a scale, for example, and you'll be able to see this when we actually do experiment too. When you kind of look through it, the prism sort of separates out basically the colors, right? And it separates out sort of like what we're talking about, kind of based on wavelength and energy. And the same thing sort of happens when you sort of see a rainbow. It happens after rain, right? And usually, and you know, those kind of the water acts almost as a prism, and it separates it out in that sort of order that we see, that sort of, you know, Roy G. Bibb sort of order. Other questions? Okay. So the significance of sort of what we've been talking about is the idea of, excuse me, that really only certain energies are allowed, as say the electron in the hydrogen atom basically sort of transitions. So, you know, the hydrogen electron will either be, say, on the first energy level, maybe it gets to the second energy level, maybe it's allowed to go from the first to the fourth energy level. And because of that, it's not allowed to sort of fall in between, like we were talking about. So again, that sort of n equals 1, which is our lowest in energy, say n equals 2, n equals 3. This electron can only be found, for example, here, or gain enough energy to get to here, or enough energy to get to here. Again, it can't find itself sort of in the middle, like a 1.5 situation in terms of energy levels. Again, it just doesn't happen that way. And that's the difference here between this quantized energy, where it's got to gain enough energy to get to here, which could be represented by that h times the frequency, or it's got to gain enough energy to get up to here. Again, it will not find itself in the middle. And that's, again, different than more that continuous spectrum where, you know, you potentially could find people or stops along the way, you know, all the way across every energy level. And again, that's why we see more of everything coming off at once when we see that more continuous one. So why is it significant that the color emitted from hydrogen emission spectrum is not white? Again, if it was white, that would imply that all the colors are coming off at once. And that would imply that it, again, is more of a continuous spectrum where you kind of see everybody sort of coming off together. And we do see these sort of distinct lines, which basically supports the idea of quantized energy, and why, as we look at a hydrogen emission spectrum, which we'll see a picture of in just a second, I think, we see these really distinct lines that represent those electrons really transitioning from one energy level to the next. So let's talk about a little bit about these energy levels and sort of what's happening. Electrons in a hydrogen atom move around the atom in this sort of circular fashion. And this is what is sometimes referred to as the Bohr model of the atom. And sort of in the Bohr model of the atom, it's sort of what is referred to as sort of a planetary model. And basically you have sort of the nucleus in the middle, and then you have this orbit, another orbit, another orbit, where n equals 1 is the ground state. Then we have, you know, for example, let's call that n equals 1. We'll call this guy n equals 2, this guy n equals 3. And the idea here, sort of what Bohr had was, you know, an electron's may be found here, and we know it's sort of traveling this pretty orbit going around in a circular pattern, or maybe the electron's up here, and it's also sort of traveling in this kind of circular pattern where, you know, you almost could kind of put your finger out there in the circle, if you want to think about it that way. And, you know, at some point it's going to come back around the circle there. But again, it would either find itself on, say, that first energy level or that second energy level. And again, the electron would either move from one energy level to the next, or maybe from here all the way out to here. Again, not stopping like in the middle of any of these sort of energy levels. So when we talk about these energy levels, as I mentioned, I think the other day, n equals 1 is sometimes what is referred to as the ground state. And that is the lowest in energy. It's also the closest to the nucleus. And anything sort of above that, like n is equal to 2 to 7, that is what is sometimes referred to as the excited states. And these are higher in energy. And obviously, as you go up there towards 7, you're kind of moving further away from the nucleus at that point. So when we look at sort of a spectrum and we see some different colors, we could think of them again as this sort of transition that's happening as the electron really, when we talk about an emission spectrum, is when those electrons are really going from higher energy levels to lower energy levels. When we talk about an absorption, so an absorption would be when they are gaining the energy, those electrons, while an emission spectrum is when those electrons are losing the energy. And that makes sense. Again, if you sort of think about it, if I have an electron here at a higher energy level, it's coming back down to a lower energy level. It needs to emit that energy. Again, the only way to go from higher energy to lower energy is to give off the energy. Vice versa, if my electron was coming in this direction, like I drew earlier, it needs to gain energy as it goes this way, which would be an absorption sort of process, or it's absorbing basically energy. So here, when we look at this, this is some of the transitions that we see in the hydrogen atom. And what we look at here, for example, is our red guy is going from the n equals 3 level to the n equals 2 level. We see our green guy is transitioning from the 4th energy level to the 2nd energy level in this example. And we see our blue guy there is going from the 5th energy level to the 2nd energy level, right? And each of those electrons in this case would be losing energy to do this. And that's why this is what would be referred to as an emission spectrum, if we would see. And each of these transitions, this transition with the red arrow, we would see on the emission spectrum a red line. And the green guy would represent a green. And obviously the blue guy would represent a blue line, which would be each of these sort of transitions that are occurring. Again, they're losing energy as they go through this. If we just think about sort of the energy to do each of those things, it does relate to sort of what we were talking about in terms of wavelength, energy, and sort of what's happening. So if we look at the red one, it's really only transitioning kind of one energy level. That's not going to be a lot of energy, which means we would expect this to be lower in energy, also have a longer wavelength in that case. Here, this guy is transitioning from the 4th to the 3rd to the 2nd. That's 2 energy levels, the green guy. That's going to be obviously a little bit more in terms of energy. If we look over here, right, a little bit higher in energy to do that 2 energy level transition. It's going to have a little smaller of a wavelength when we see it come out, as opposed to our last guy here, which is transitioning from the 5th to the 4th, which is 1 energy level, 4th to the 3rd is 2 energy levels, the 3rd to the 2nd is 3 energy levels. That's going to require a lot more energy to do that transition. Also, we would expect more of a smaller wavelength over here. So, you know, when we would be looking at this, say through a prism, where it would sort of separate out everybody, and usually when you look at it through a spectroscope, like we're going to do an experiment to, you know, there's like a little ruler basically in there of wavelength, and we would expect the higher wavelength over here where we would see that red come out, and again, that sort of shorter wavelength on this edge when we would see that blue color basically come out. Any questions on that? So this is a much prettier picture than what I drew of really Bohr's model of the atom. And Bohr's model of the atom, or Bohr's theory of the atom, is a model that, our theory, like we talked about, that, when we talk about a theory, it is something that may not be correct in all aspects. It may be later disproven. Parts of it is correct and parts of it is not correct. And that's really sort of what we see here with Bohr. It was sort of proven that, it works really well when we're talking about sort of hydrogen and the lines that we see associated with hydrogen. Hydrogen, again, has basically one electron. So it works really well in explaining sort of what's happening. It doesn't really hold up as we move past hydrogen and things that have multiple electrons. So it works really well for hydrogen, not so well for things past hydrogen. And also, as we'll talk about later in this chapter, this is also why we kind of move away from Bohr's idea of the atom like this as sort of this planetary model where we think about electrons move in these circular paths, to, as we'll talk about a little bit later on this chapter, the idea that really we don't know how an electron is moving. We don't know, sort of the path it's taking, how fast it's moving. And we don't really talk about electrons being in orbits, but they're more in what are known as orbitals, which you might be familiar with or remember, things like s orbitals, p orbitals, d orbitals, and so forth. And again, as we talk about that later in this chapter, we sort of move away from this idea. But again, as a couple of points here, we see our blue guy as our transition. And again, it's going to be sort of that quantized energy where it has to gain a certain amount to do that. Same idea here. This guy's got to gain a certain amount to do that. And again, in terms of exothermic and endothermic that we talked a little bit about today, as the electron goes from a higher energy level to a lower energy level, again, it's got to come down in energy. It's got to give off that energy in the form of a photon of light. And that is an exothermic process for the atom. And if we were to calculate the energy of that atom as it goes through that process, we should really end up with a negative number, because that's what we would expect. Again, that energy is not going to be lost. So that atom is going to be giving off that energy that electron is losing really to the surroundings. And vice versa, if we go sort of the opposite way, if we take our electron and go from we go from a lower energy to a higher energy, energy actually has to be absorbed by that electron. And that is an endothermic process, where again, heat and energy would be absorbed by the atom. And if we were to calculate the E for that, or the energy associated with that process for the atom, it would be a positive number, our endothermic. Any questions on that there? So how can we calculate, sort of what is going on, in terms of energy for these transitions that occur for these electrons? There is a formula that we use to sort of calculate the energy associated with an electron as it's transitioning from one energy level to the next. And it is this equation here. The change in the energy of the atom is equal to minus 2.178 times 10 to the minus 18 joules times 1 over n squared final. That's the final energy level squared, minus 1 over the initial energy level of the electron. Now, I personally also round on this number as well. So the change in the energy minus 2.18, I personally kind of round to that number. You could use that big number. I think in your lab, it uses the big number, n squared final minus 1 over n squared initial. And a couple of things here about this change in energy is the same as we just saw, which is h times the frequency. and it's also hc over the wavelength. So you could tie this equation into those couple that we saw previously. And again, this allows you, if you know about an electron, for example, just the transitioning that's happening, you could figure out the frequency of that photon of light that's coming off. You could also figure out the wavelength of that guy coming off as well. So, and again, that goes back to the same E that we saw earlier, H times the frequency, HC over the wavelength. So this guy and this guy is the same in this sort of situation. And you can calculate things like what the wavelength is, what the frequency is of the light that's coming off, or the photon of energy that's coming off there for the electron as transitions. One really important thing that people kind of screw up on when they're using this formula is this negative. So you should definitely use the negative in the calculation, but let me just explain three things that we typically calculate. One is energy, one is frequency, and one is the wavelength. When we calculate the energy for something like this, you want to make sure that you keep the sign. And what I mean by that is if you calculate it and it's a positive number, you should keep it as positive. Or if you calculate it and it's a negative number, you should keep the negative sign. The positive number for energy tells us that overall this process is endothermic for the atom, while the negative, as we just talked about, would tell us that it is exothermic. Now, once you calculate the energy, that's maybe positive or negative, but more importantly, if it ends up being negative, which it oftentimes is in an emission spectrum, because it has to give off that energy, so it should be negative. When you would then use that energy value to calculate something like frequency in this case, or maybe wavelength, you want to turn your energy into a positive number. So when you calculate something like the wavelength of a photon or the frequency, this does need to be a positive number. And sometimes people, when they calculate the energy, that's negative and they use it in, say, this version of the equations as well, they end up with a negative frequency and a negative wavelength, and you can't do that. So it has to be a positive value for wavelength, a positive value for frequency, but the energy, you should leave it as either positive or negative. So important in terms of the sign for energy to keep the sign. But if you are then going to use that number in a calculation to continue on to calculate something like wavelength or frequency, just make it a positive number and make sure you end up with a positive number for wavelength or frequency. Any questions on that? We're going to do a couple examples and hopefully it'll make more sense, but any questions up to that point? So as I mentioned, Bohr's model worked really well, sort of for what we see in terms of those sort of four lines for hydrogen. It does sort of fall apart when we get more electrons involved rather than just one. But it nicely sort of shows that quantized energy, but not so good for anything outside of, obviously, hydrogen that has more than one. And as we'll talk about a little bit more in this chapter a little later, again, those electrons really don't move around the nucleus in a circular fashion. And again, that's why later we'll see we don't talk about orbits. We talk about the idea of electrons being orbitals and the idea that electrons are really just kind of moving around randomly about the nucleus. They are definitely not, as Bohr sort of suggested, moving in these pretty circles where, again, you could just kind of wait right about here and, eventually maybe the electron will come back around, and it doesn't really happen in that fashion. It does basically move pretty randomly about. Any questions on any of that there? All right, so let us do some calculations of all this stuff we just talked about. So in this particular one, we want to know what color is emitted when an excited hydrogen atom goes from n equals 5 to n equals 2, n equals 4 to n equals 2. n equals 3 to n equals 2. Why don't we, for each of these though, let's add a few things just to make sure, because this will be very similar calculations to what you need to do in experiment 2. So it'll be good to practice these. So for each of these, calculate the energy associated with that photon of light, the wavelength, and let's do the wavelength in nanometers for this one, again, because it's part of the visible spectrum. And let's do the frequency as well. Nanometers, again, a reminder, nano is 10 to the minus 9. Also a reminder, C is 3 times 10 to the 8. And obviously in this case, we're doing transitions for each of these. So you do want to use the equation we just saw, that minus 2.18. This guy right here would be probably the one you want to use. By the way, this number here as well, this 2.18, that is also sometimes referred to as the Rydberg constant, just for a reference point. But again, you want to kind of use this guy, and we do want to figure out wavelength, frequency, and energy for each of those. Any questions on that there? So tell you what we'll do, since these are again going to be very much like the calculations we do in experiment 2, we'll take about 10 minutes or so. And what I'll do is I'll open up some breakout rooms in case you want to work on it kind of together and see what you come up with for each of these. And then we'll come back together and we'll talk about what everybody got here. So what we do, definitely pretty much the calculations that you're going to have to do there on experiment 2. So let's make sure everybody is on the same page. So we're going to take each of these sort of separately. We'll start with A, which again is a transition from the 5th energy level to the 2nd. So we'll start with that one. Let's take a look. So we're going from n equals 5 to n equals 2. So just in general, what's happening here is obviously we are transitioning from a higher energy level to a lower energy level. So the electron is dropping back down. As a result, it will give off the energy in the form of a wave. And just by knowing it's going from 5 to 2, we should know that it is going to be exothermic in that case. And we also know that energy probably should be a negative number because of that transition that's going to be happening. So these are ways we could kind of check to make sure, we're sort of, doing things correctly and sort of have the right idea here. All right, so we want to use the equation that we saw, which is the change in energy is equal to minus 2.18 times 10 to the minus 18 joules. 1 divided by our n squared final minus 1 divided by our n squared initial. And in this case, again, remember that it's starting on the 5th energy level and it's ending up there on our 2nd energy level, which is our final. And joules. So that would get us something like minus 2.18 times 10 to the minus 18. 1 over our final, which is 2. That is our final, right? So 1 over 2 squared is 4, minus 1 over our initial, which is 5 squared, which is 25. Did something that made it unhappy here. All right, sorry about the extra lines. All right. So putting all that into our calculator should get us something like minus 4.58 times 10 to the minus 19 joules in this particular case. So that should be the energy that's associated with that transition. Any questions on that calculation? Again, we want to make sure that we are using our exponent button in this particular case to get us this answer here. As I was mentioning earlier, when you do calculate the energy, You want to make sure you keep the negative here. And as we predicted up there, we did predict that it should be a negative value for energy, telling us that it is exothermic, then heat and energy is being given off by the atom. Again, as that electron comes down in energy, it needs to give off that energy in the form of a photon of light. Any questions on that there? Now we also want to calculate the wavelength and the frequency. And that's again where we could kind of tie in some of our earlier sort of formulas, that E is equal to H times the frequency, which is equal to HC over the wavelength. And in this case, we could just go with the first part, which is the E is equal to H times the frequency. Since we already now calculated the energy, remember H is a constant, which is Planck's constant. That is that 6.63 number. So rearranging this, we would get that the frequency is equal to E divided by H. And this is where we do want to turn that negative into a positive. So remember that when we calculate the frequency or the wavelength, it does need to be a positive number. So our energy being 4.58 times 10 to the minus 19 joules divided by our H, which is Planck's constant. In this case, the joules will cancel each other out, and that's going to leave us reciprocal seconds that's left over, and we will end up with 6.91 times 10 to the 14 reciprocal seconds here as our answer. Any question on those numbers there? So we now have our frequency, and get rid of some of those extra lines and fix it up real quick. 19 divided by 34. All right, and reciprocal seconds. Now that we have the frequency, we can do one of two things here. We can use our E is equal to HC over the wavelength, or we could use C is equal to the wavelength times the frequency. Again, at this point, we have the frequency. Speed of light is a constant. So if we did that approach, the wavelength would be C divided by the frequency. And again, that would give us 3 times 10 to the 8 meters per second divided by our frequency, which is 6.91 times 10 to the 14 that we just calculated. Reciprocal seconds and seconds will cancel. That is going to give us 4.34 times 10 to the minus 7 meters. And remember, we wanted it in nanometers. So we would take 4.34 times 10 to the minus 7 meters. And again, using our nano conversion, 10 to the minus 9 meters is 1 nanometer. And that's going to give us 434 nanometers for the wavelength. And just to show you again, you could use this formula here. You could rearrange and solve for the wavelength, would be HC divided by the energy. Again, H being our 6.63 times 10 to the minus 34 joule seconds. RC being our 3 times 10 to the 8 meters per second divided by our energy, which again, we would use as a positive number. Joules would cancel, seconds would cancel. We'll end up with the exact same answer again if you went sort of that fashion as well. So again, there's a couple of different ways that you could get to the same answer. They both should get you pretty much the same place as long as you punch them in correctly. Any questions on any of that there? By the way, 434 is somewhere in the, what is that? That's probably like a bluish type of color. Any questions on any of those numbers, where any of those numbers came from?
Can you repeat one more time why you changed the negative to a positive
Yeah, so when we
for the
went from minus 4.58 times 10 to the minus 19.
yes.
Okay. So when we're calculating something like energy, which was the first thing that we did, where we have the negative 4.58 times 10 to the minus 19, you absolutely should leave the negative for the energy calculation and answer. Again, the negative tells us that it's exothermic, and overall, this atom is giving off that heat and energy as the electron is dropping back down from the higher energy level to the lower. Overall, the atom is releasing that energy, which is exothermic, and why it's important to keep the energy value with the negative. But when we go to use that value in either, say, this calculation here, or we use it maybe down here in this calculation, we want to turn it into a positive number, because if we did not, the only difference that would happen is we would end up with a frequency of minus 6.91 times 10 to the 14, or a wavelength of minus 4.34 times 10 to the minus 7. Now, whenever you calculate the frequency or the wavelength, both of these numbers need to be positive numbers. And that's why we do need to get rid of this negative here. So the only thing that is sort of okay in this sort of set of calculations to leave as negative is the energy, because the negative value or the positive value for an energy number tells us what is happening in terms of, is that thing exothermic or endothermic? So the easy way to remember is you can't have really a negative wavelength or a negative frequency. It needs to be a positive number. And again, it's not super critical in the sense of, if you left the negative, you would get a different number or anything like that. You would just get the negative version of the number, and it technically would be wrong because it should be a positive number for both frequency and wavelength. Other questions on any of the numbers or where we got anything from?
Thank you.
You're welcome. Okay, so that was the first one. That was going from 5 to 2. So let's take a look at the next one, which is going from 4 to 2 in this case. So going from 4 to 2. So our n is equal to 4 to n is equal to 2. Again, here 2 being our final. So we'll start with the same sort of process. Again, we're going from higher energy to lower energy. So just like the last one, we could predict that this energy should be a negative value in exothermic. So might as well plug it right into that equation. And again, we want to make sure that we do use our exponent button when we're punching these numbers in. So 1 over 2 squared is 4, minus 1 over 4 squared, which is 16 in this particular case. That looks like it gives us an energy of minus 4.09 times 10 to the minus 19 joules. Again, here we do see the negative value, which we did expect it to be exothermic for the atom here, as the electron again is going from higher energy to lower energy. In order to do that, it has to give off the energy in the form of a wave. And again, you have you could go into the frequency if you want first. You could do wavelength if you want, but at this point, I might as well go with frequency. Again, solving for frequency is R E over H. Again, turning our energy into a positive number so we do not get a negative frequency, divided by H, which again is a constant. So you always have this number available to you, the 6.63 times 10 to the minus 34 joules times seconds. Again, the joules are going to cancel. That's going to leave us the reciprocal seconds. And I believe 6.17 times 10 to the 14. Again, reciprocal seconds being our frequency at this point. And as we saw in the previous one, you had a couple of ways to get to the wavelength. Perhaps again, using this one might be the simplest at this point. The wavelength, which is the lambda symbol here, is equal to c divided by the frequency. And that's going to be 3 times 10 to the 8 meters per second divided by our frequency we just calculated. Again, seconds and reciprocal seconds will cancel out, and that will leave us the answer in meters. And again, making sure you use your exponent button there. You should end up with 4.87 times 10 to the minus 7 meters. Again, using our conversion between meters and nanometers. We have our 10 to the minus 9 meters is a nanometer. So essentially we're dividing that 4.87 times 10 to the minus 7 by 1 times 10 to the minus 9. And that's going to give us 487 nanometers, somewhere in that greenish part of the visible part of the spectrum. Any questions on that particular one there? Okay. That leaves us the last one, which is C, which obviously we will approach the exact same way here. So this last one, what are we doing on that last one there? We are going from 3 to 2, looks like. So n is equal to 3 to n is equal to 2. Not a giant transition here, but still going from higher to lower. So again, we should expect the energy of the atom to be exothermic here. So starting just like we did the others, our change in energy, minus 2.18 times 10 to the minus 18 joules. Again, this is what is sometimes referred to as Rydberg's constant. The 2 here also going to be our final. So 1 over 4 minus 1 over 3 squared, which is 9. And it looks like in this particular case, we end up with minus, again, as we would expect, 3.03 times 10 to the minus 19 joules. Any questions on that one there? And again, following kind of the same approach, I'm going to go this way with it, which would give us that the frequency, actually I went the wrong way. We'll go with what we did before. E is equal to h times the frequency, which will give us our frequency is equal to E divided by h. So again, turning our energy into a positive number so we don't get a negative, divided by our Planck's constant, which we always have. And just like previously, joules cancel, going to give us 4.57 times 10 to the 14 reciprocal seconds. And just to mix it up here, why don't we go with this way of doing this last one? And again, solving for wavelength is hc divided by the energy. Just to show you again, you could get it a couple of different ways here. Again, that's being our h, which is our Planck's constant, our speed of light, also a constant. And in this case, it's again, we're using the energy. We're going to make it positive so we don't end up with a negative value. Everything cancels out except for the meters. And it looks like we do end up with 6.57 times 10 to the minus 7 meters, converting us into our nanometers. Going to be 657 nanometers in this particular case. Orangey red, I guess, somewhere in that case would be the color associated with that. Any questions on any of those calculations? It is definitely something that you need to be able to do. as we are definitely going to be doing a lot of those calculations, especially in experiment 2. Any questions on when any of those came from? Just to answer one of the last questions, I think that was actually on it, was what transition is the longest wavelength? So we would expect the longest wavelength here to actually be the one we're looking at, right? So the longest wavelength is actually this one here is the longest wavelength. 657 versus 487 and versus 434. And what we see in terms of energy is what we thought about and talked about. The energy of our shortest wavelength is 4.58 versus 4.09 versus 3.03, which is the smallest in energy, along with our longest in wavelength. So we do see number-wise what we talked about, that the longer the wavelength, the lower the energy, and the shorter the wavelength, which in our case was this first one, the higher the energy value is, as you can see. Again, because it's really making a longer transition in terms of energy, it's got to go through multiple energy levels, going to result in more energy and a higher frequency to do that, and higher in our shorter in wavelength. Any questions on any part of any of those calculations? And again, if you see yourself kind of close to the right answer, but the exponent part is off, it is probably the way you are punching that into your calculator. Any questions? Everybody's good? Professionals? Like it? Okay, so I think that's definitely enough torture for today, I think, right? So we will obviously stop there for now. We will continue to lecture on Thursday through chapter 2, maybe into the next chapter after that. But let's talk about a quiz. We probably should do one before I forget to ever give you a quiz. So let's go with... let's do a quiz next Tuesday, whatever date that is. What is that? It's the 22nd, maybe? No, 23rd, maybe. Give or take a day, whichever day is right there. And it will be on all chapter 1 and chapter 2 up to today. So whatever we covered up through these calculations we just did up to today. We will probably take it either at the end of lecture on Tuesday or at the beginning of lab on Tuesday. I'll let you know for sure. I'm still deciding which way we'll do it. It will probably be done through, obviously, a Zoom meeting where you do need to have your camera show you and your work area. And that's probably how we will do it. So I'll give you more information, obviously, maybe on Thursday as well. But that's sort of tentatively what's going on. So chapter 1, all of it, and chapter 2 up until what we just talked about today here right now in these calculations. No, we probably won't review, to be honest with you. So you'll get a lot of review on what we just did come Thursday, because pretty much those 3 calculations we just did, you're going to do 1,000 of them. Hopefully not 1,000, but there's a lot of those calculations you're going to have to do for the experiment. So you'll get a lot of practice definitely this coming Thursday when we do lab. So again, this Thursday we'll continue lecturing. We will do experiment 2 on Thursday, which again will help you review all this stuff. Other than that, any questions on anything? Okay, other than that, I'm good. If you're good, make sure you put here if you haven't done so. If you still have questions on anything, I'll be happy to answer. Otherwise, have a good night, and I'll see everybody on Thursday.